I'm Matthew Marko. I'm from the 2010 SMART cohort. I went to Columbia for my PhD. I work on the advanced arresting gear. The new Ford-class carrier, which I'm sure many of you have heard about, it has a whole new launching mechanism and a whole new arresting gear and many other new things. And the launcher and the arresting gear, because it's an aircraft carrier, are the most important part of it. And the arresting gear itself, previously we used hydraulic pistons. This one uses a big water twister with a motor to fine-tune it. In theory, you'd have more control, it'd be a smoother catch, but of course, any new technology, there's new issues, new things to discover. This twister, of course, has ball bearings, and my experience at Columbia, helped me to better understand the tribology, the lubrication, rollers, and contact, and it's a huge amount of load, and most interestingly, most ball bearings are going to spin constantly. Right now, I have a quick, approximate study using I approved the ball bearings that are currently going to be in use, and I'm hoping to study them further, and there's a lot to it. And my knowledge at Columbia helped me understand these bearings. So what did I do at Columbia, which is the basis of it? Now, tribology is the study of friction and wear. Most of my tests were what we call a 4-ball test. As you can see, you have 4 identical ball bearings, 3 are locked in place, you coat it with an oil of interest, and the 4th ball, same ball, locked in place, it's under a load, spins at a set speed, and whatever the wear score, as you can see that little hole that'll form, the amount of wear, the diameter, the chemical properties, you can learn about the lubricant. So what I did unique, now this test is not new, that's been around for a while. What I did unique is I studied putting diamond dust into the oil, which I was told improved the oil. This is counterintuitive. You would think putting, diamond, which is hard, in oil is just going to make more scratches, more wear. Now, I only did a very tiny amount. First of all, these were nanoparticles, 10 to 50 nanometers as best we could tell. And of course, we dealt with very small concentrations, 1% of 1% mass concentration. So throughout my time at Columbia, I did a whole series of these 4-ball tests with both mineral oil and oil additive. I did it in different temperatures and speeds and loads. And basically, I also built a finite difference model which basically used iteration as best I could, to predict how the ball would deflect, what the existing wear was, and basically try to model ultimately I wanted to know what the lubricant profile was at the point of contact. And if I know this, I know how much wear is happening because for a given random asperity height, Greenwood-Williams, there's going to be heights, when you have random roughness that exceeds the lubricant thickness, it shears off. Now, how does diamond being mixed in there improve the oil? As best I could tell, and of course I can't see what's going on, we're talking nanometer scale, but as far as my model, which the experiment was experiment validated, diamond is very thermally conductive. Oil is a thermal insulator. You put the diamond in this oil, the oil will still be maybe 40% more thermally conductive. The oil is more thermally conductive. The heat that's generated from friction at the point of contact, is conducted away quicker. It's cooler. The oil's cooler. It's more viscous. It becomes thicker at this point of contact, and you have better protection of your surfaces.